Hello friends, today we will gain knowledge about the earthquakes. Friends, let me first introduce you the term earthquake. An earthquake is a natural phenomenon like rain. In simple terms, earthquakes are caused by the constant motion of Earth's surface. This motion creates build-up and releases energy stored in rocks at and near the Earth's surface. Earthquakes are the sudden rapid shaking of the earth as this energy is released. Seismology, derived from Greek word seismos meaning earthquake and logos meaning science, is the science of earthquakes and related phenomena. Seismograph is an instrument that records the ground motions. Seismogram is a continuous written record of an earthquake recorded by a seismograph. Earthquakes affect almost every part of the earth and they can be either mild or catastrophic. An earthquake may last only a few seconds, but the process that cause earthquakes have operated within the earth for millions and millions of years. Until very recently, the causes of earthquakes was an unsolved mystery. In the mid-1960s, many scientific observations and explanations of earthquakes came together in the theory of plate tectonics. Thus, it may be defined as a sudden, rapid shaking of the earth caused by the release of energy stored in rocks. Now friends, let's learn about the origin of earthquakes. Because strong earthquakes have such disastrous effects, it's not surprising that people have always looked for ways to explain their origin. We have learned in recent years, largely from the study of earthquakes, that the earth around us is not static like a stage set for a play. The earth's crust is a rocky layer of varying thickness, ranging from a depth of about 10 kilometers under the sea to 65 kilometers under the continents. The crust is not one piece but consists of portions called plates, which vary in size from a few hundred to thousands of kilometers. The Earth's rock layer is broken into large pieces. These pieces are in a slow but constant motion. They may slide by smoothly and almost imperceptibly. From time to time, the pieces may lock together and energy that accumulates between the pieces may be suddenly released. This sudden release of energy, like the snapping of a rubber band that has been stretched too far, is what we call elastic rebound. Energy is released and travels through the earth in the form of waves. People on the surface of the earth experience an earthquake. If the stress is along a fault, some of the released energy causes the rocks to slip along the fault plane, rupturing the fault. If there is no fault, the released energy will fracture the rocks to create one. The remaining energy is released as seismic waves and earthquake. Plate tectonics is the theory that the surface layer of the earth, the lithosphere, is broken into blocks that move horizontally with respect to one another over a soft, pliable region of earth, the asthenosphere. The lithospheric blocks are called plates. Plates move at 1 to 10 cm per year and have moved vast distance in the earth's 4.6 billion year history. Plates can and usually do contain both continental and oceanic material. There are approximately 7 major and 12 minor plates. The theory of plate tectonics holds that the plates ride up on the more mobile mantle and are driven by some yet unconfirmed mechanism, perhaps thermal convection currents. Even these plates contact each other. Stress arises in the crust. These stresses can be classified according to the type of moment along the plate's boundaries: pulling away from each other, pushing against one another, and sliding sideways relative to each other. All these moments are associated with earthquakes. The areas of stress at plate boundaries which release accumulated energy by slipping or rupturing are known as faults. Faults can be recognized by offsets of horizontal layers, scarps, offsets of natural horizontal features like ridges and streams, offsets of man-made features like roads, fences, etc., juxtaposed rocks on the surface, and earthquakes. Faults are classified as either strike slip or dip slip. The fault plane for strike slip fault is usually vertical. These faults can be subdivided into left lateral and right lateral strike slip faults depending on the direction of the motion of the blocks across the fault from the observer. Dip slip faults are further subdivided into normal faults and reverse faults. The direction of movement of dip slip fault is given relative to the hanging and foot walls of the fault. The fault rupture generates vibration called seismic waves, which radiates from the focus in all directions. The point of rupture is called the focus and may be located near the surface or deep below it. The point on the surface directly above the focus is termed as epicenter of the earthquake. Dear friends, let us discuss about the methods for determining the location of an earthquake. The method of locating the focus and epicenter of an earthquake by drawing three spheres, each centered at the seismic station with the radius of the calculated distance from the station to the quake, is called triangulation. The intersection of three spheres indicates the focus. After calculating the distance from the seismic station to the epicenter, the next step is to draw a sphere with the radius, that is the distance from the seismic station. The ability to determine the focus and epicenter of an earthquake has made it possible to map both location for an earthquake recorded by seismographs. Over time, the mapping has revealed two facts. Most earthquakes occur at the plate boundaries and most earthquakes occur less than 65 kilometers beneath the surface, with the deepest earthquakes occurring at about 640 kilometers beneath the surface. Now, let's discuss about earthquake depths. About 75% of all earthquakes occur between the Earth's surface and a depth of approximately 65 km. These are known as shallow focus earthquakes. Another 20% of all earthquakes referred to as intermediate focus earthquakes occur at the depths from about 65 to 300 km. The remaining 5% of earthquakes, called deep focus earthquakes, takes place between 300 km to about 640 km. This rather uneven distribution of earthquakes is easily explained by the fact that an earthquake can only occur where rocks are brittle. Thus, most of the intermediate and all of the deep focus earthquakes occur at convergent boundaries featuring subduction zones. The most obvious indication on a seismogram that a large earthquake has a deep focus is the small amplitude of the recorded surface waves and the uncomplicated character of the P and S waves. Types of earthquakes. There are three different types of earthquakes: tectonic, volcanic and explosion. The type of earthquake depends on the region where it occurs and the geological makeup of that region. The most common are tectonic earthquakes. These occur when rocks in the Earth's crust break due to geological forces created by movement of tectonic plates. Another type, volcanic earthquake, occurs in conjunction with the volcanic activity. Collapse earthquakes are small earthquakes in underground caverns and mines, and explosion earthquakes result from the explosion of nuclear and chemical devices. Now, types of earthquake waves. Earthquakes produce various types of seismic waves that cause rocks to vibrate or shake as they propagate through the earth. Waves are characterized by wavelength and amplitude. Wavelength is also inversely related to frequency. Seismic energy from an earthquake radiates out in all directions and propagates through the earth. The path of energy can be traced with ray fronts like ripples on a pond or ray paths which are perpendicular to the ray. Earthquake produce both body waves which travel through the earth and surface waves which only travel on its surface. Body waves travel faster than the surface waves. There are three types of waves that are created when stress is released as energy in the earthquakes: P, S and surface waves. The P wave or primary wave is the fastest of the three waves and the first detected by seismographs. They are able to move through both liquid and solid rocks. P waves like sound waves or compressional waves, which mean that they compress and expand matter as they move through it. S waves or secondary waves are slower and propagate as shearing motion perpendicular to the direction of the wave. S waves cannot travel through fluids like the outer core because the fluids are not elastic to shear forces. S waves are the most dangerous type of waves because they are larger than P waves and produce vertical and horizontal motion in the ground surface. Both P and S waves are called body waves because they move within the Earth's interior. Their speeds vary depending on the density and the elastic property of the material they pass through, and they are amplified as they reach the surface. The third type of wave and the slowest is the surface wave. These waves move close to or on the outside surface of the ground. There are two types of surface waves: love waves and Rayleigh waves. Love waves that move like S waves but only horizontally and cause the surface to move perpendicular to the motion of the wave. The Rayleigh waves that resemble water waves and move both horizontally and vertically in a vertical plane pointed in the direction of travel. Measuring the severity of quakes. Whenever a quake occurs, there are two questions on everyone's mind: where was it and how big was it? The size of an earthquake is a reference to its strength. There are two methods scientists use to describe earthquake strength: intensity and magnitude. The intensity of an earthquake describes the impact of its shaking on both humans and objects. The Italian seismologist Giuseppe Mercalli developed a 10-point scale called the Mercalli intensity scale that described the intensity of shaking based on its impact to human beings and property. The scale was later modified to 12 steps and is called the modified Mercalli scale. The magnitude of an earthquake is the number most often referred to in news reports regarding the size of an earthquake. Magnitude refers to the amount of energy released based on ground movement detected by seismographs and is expressed as a value on the local magnitude scale. This scale is commonly referred to the Richter scale because it was devised by seismologist Charles Richter in 1935. The greater the energy release as evidenced by ground movement, the higher the magnitude. The Mercalli scale of earthquake damage measures the intensity of an earthquake at a particular place. It uses the type and amount of damage. Unlike the Richter scale, it does not measure the absolute strength of the earthquake, but how strongly it is felt at a particular place. The types of damage caused by earthquakes. Only a small portion of earthquakes that occur annually around the world are headline grabbers. In most cases, that is because of their impact on life and property. In fact, most earthquakes are either too small to be of concern or occur in a relatively uninhabited area. As noted earlier, earthquakes are concentrated near plate boundaries. When a plate boundary is in a populated area, the earthquake is more likely to be a damaging one. Building collapse. People can be trapped in collapsed buildings. This is the type of the damage that leads to the worst casualties. Buildings that can otherwise withstand the quake can be knocked off their foundations and severely damaged. Landslides. Buildings can be damaged when the ground gives way beneath them. This can be in the form of a landslide down a hill or liquefaction of soils. Ground movement can change the whole landscape. Fire. Fires often break out following earthquakes. Fires can easily get out of control since the earthquake. There are many demands made on the emergency response system that slow down response to the fires. Tsunami. Underwater earthquakes, volcanoes or landslides can produce a tsunami or tidal wave. This wave can travel very rapidly thousands of miles across the ocean. In deep water, the tsunami may only raise the ocean level by a few centimeters, hardly enough to notice. But as it approaches land, the shallower water causes the wave to build in height to as much as 10 to 20 meters or more and suddenly flood coastal areas. Tsunamis carry a lot of energy, and when they hit the coast, strong currents can cause massive erosion of the coastline as well as tearing apart buildings it encounters. Typically, a tsunami will last for a period of hours, with successive waves drastically lowering and raising the sea level. Although scientists now understand the causes of tsunamis, there are many local factors including the slope of the sea floor at a given location, the distance and direction of travel from the earthquake that will determine the severity of the resulting wave. The factors contributing to earthquake destruction. One of the changes that occur during the rock cycle is the weathering of rock into sediment that is then carried away to accumulate elsewhere. Sometimes this sediment is loosely packed and referred to as unconsolidated sediment. In other areas, the sediment has been packed together enough over time to become almost rock-like. This is called consolidated sediment. There are other areas in which underlying bedrock is exposed at the surface. Liquefaction. Water adds an additional dimension to the instability of unconsolidated sediments that may otherwise seem solid. When the particles in water-saturated sediment are dry, they rest on each other and hold each other in place. But if those particles are saturated with water, the water can act as a lubricant. When the ground starts shaking, the sediment loses the cohesion altogether and turns the quicksand in a process called liquefaction. The conversion from seemingly solid ground to quicksand is so sudden and complete that water is often seen spurting onto the surface during an earthquake, sometimes creating holes in the ground called sand boils or sand volcanoes. How can we prevent the earthquake damage? The first protection against earthquake risk is zoning, which restricts the type and density of structures in vulnerable areas. Framed structures fail during earthquakes because they flex at their joints and can be stiffened with the addition of shear walls. Shear walls are reinforced panels designed to resist strain which occurs during shaking and swaying. A second approach to building earthquake-resistant buildings is base isolation, in which structures are set atop flexible mounts which do not transfer ground shaking to the structure. Construction standards. Seismic retrofitting is the modification of structures to better withstand earthquake stresses. One change that has become standard for new houses is the requirement to bolt the structure to its foundation. A common aftermath of earthquakes involves buildings that have fallen off their foundations. In reality, the horizontal movement of the lava waves pulled the foundation out from under the buildings. Bolting the foundation to the structure keeps this from happening. Another practice is to reinforce crawl space between the floor and the ground with solid plywood. Material that bends rather than breaking is favored for construction. For instance, wood over brick. If a brick building is desired, then heavy concrete supports reinforced with steel rebar is added to allow the buildings to flex during earthquakes. Base isolation is used for larger buildings. In this case, the building is constructed on a foundation containing springs or rubber that would absorb the shock and ground movement of even large earthquakes, isolating the energy of the earthquake from the structure. Most of these steps are requirements for new structures. In addition, existing structures can be retrofitted to meet these standards. Thousands of homes in seismically active areas have been modified to be more earthquake resistant. Liquefaction mapping. In addition to building better structures and reinforcing old ones, seismologists and geologists are actively mapping areas to better predict the impact of earthquake in those areas. Of particular interest are liquefaction hazards, which are now part of the geological analysis that take place before new projects are approved. Knowing whether an area is subject to liquefaction can help residents in their home buying decisions and in the development of their emergency plans. It also provides data for disaster teams in determining where the most assistance is likely to be needed. Liquefaction mapping is also useful in land use planning because it has been long known that buildings with foundations anchored into bedrock have the best chance of surviving an earthquake, while those built on fill, especially waterlogged fill, have the highest level of damage. The construction of new commercial or residential developments on such sites is either discouraged or prohibited. Earthquake prediction. Hundreds of millions of people who live in the world's seismically active areas would be delighted and relieved to receive an accurate prediction of when and where the next large earthquake will strike. So far, seismologists have not been able to accommodate them. They are, however, conducting the research that may one day lead to the ability to better predict earthquakes. Such research depends first on the accurate collection of data. Earthquake forecasting is limited to long-term prediction expressed in terms of probability over a number of years. The worldwide seismic network provides data that allows seismologists to identify the strength and location of the earthquakes around the world, providing data that can then be analyzed for patterns. The field of paleoseismology, the study of ancient earthquakes, looks for patterns of past events in order to identify areas of seismic gaps, segments along faults that are overdue for an earthquake and along which pressure is highly likely to be building. Short-term predictions, those that would forecast an earthquake due in a few hours, days or weeks, are not yet possible. Friends, we conclude our topic with some important points. Earthquakes occur when rocks release stress according to the elastic rebound theory, which states that pressure due to plate tectonics are stored in rocks, which respond elastically. When the elastic limit is exceeded, the rocks slip along the fault or break to create one. releasing energy in the form of seismic waves. The focus and the epicenter of an earthquake are located through triangulation using the time travel chart. Earthquakes are measured in terms of intensity and energy release. Hope you have understood today's topic. Thank you.